So in this video, we will discuss the banana problem from the 2017 AP Calculus exam. This was number 2. It was a free response question that allowed you to use a calculator. And if you read the problem statement, a grocery store opens and it has 50 pounds of bananas on a display table. Customers are going to be removing those bananas from the display table at a rate modeled by f of t, holds on the interval from 0 to 12. F of t has units of pounds per hour. T is measured in hours after the store opens. After the store has been open for 3 hours, store employees start adding bananas to the display at a rate modeled by g of t. Now this only holds from 3 to 12, right? It doesn't start until 3 hours into the day when they start restocking the bananas. And then it's got the same units as f of t, measured in pounds per hour. T is measured in hours after the store is open. How many pounds of bananas are removed from the display during the first 2 hours the store is open? So we don't care about how many we start with. We don't care about the restocking. That hasn't even started to happen yet within this time frame. We just care about how many bananas are removed. And so if this is the rate that the pounds of bananas are being taken from the display table by the customers, we're going to have to integrate that rate of change across the appropriate limits of integration in order to build that answer. And if you break out the calculator here, here's my TI-83 input that you see screenshotted to the bottom of the screen, and then rounding that to the third digit beyond the decimal gives you 20.051 pounds of bananas removed from the display over the first 2 hours that the store has been open. Part B asks you to find f prime of 7. Using correct units, explain the meaning of f prime of 7 within the context of the problem. So if you look at this function, f of t, it's something that you can take the derivative of by hand. The derivative of 10 is 0. The derivative of this, well, that's going to get a little dicey because you're going to have to use a product rule. You're going to have to finish that product rule with a chain rule, and that's fine. You can definitely do this piece of the problem that way. But if the calculator is in play, you can definitely cut down on length of the problem. You can cut down on the amount of risk that you're taking, the amount of places where you have the opportunity to make a mistake by breaking out the calculator. In the calculate menu of a TI-83 or a TI-84, you can grab the numerical derivative option. This won't find the derivative for you in general, but it will evaluate the derivative at 7. And that's all we need here. We don't need the derivative with respect to t in general. We just need to know the value of the derivative evaluated at 7. Numerical derivative option does that pretty well. We type in the function that we want to take the derivative of first, give the calculator a comma, give the calculator the variable that we're going to differentiate with respect to, and as you see, I typed x into my calculator, so that's what I went with there. Another comma, the value that we would like to evaluate the derivative at, which in this case is 7. Rounding that to the third digit beyond the decimal gives us negative 8.120. Does ask you for units, right? So the units of this function are pounds per hour, right? And we've done the derivative with respect to t. So on the y-axis, if you graphed f of t, you'd have pounds per hour. On the t-axis, you'd have hours. So we're looking at pounds per hour, or pounds per hour squared for the units of this computation. Now the interpretation. What does this mean within this context? So this is a function that represents the rate that the bananas are being removed. So I said the rate at which the bananas are being removed from the display table, it's decreasing by this many pounds per hour at t is equal to 7. And I guess the one thing that you will notice here, I didn't copy this number into my explanation. I used the word decreasing that indicates that the value is negative. So that's the significance of the sign of that rate of change. Part C is the number of pounds of bananas on the display table increasing or decreasing at time 5. Give a reason for your answer. Pretty simple logic here. How quickly are the bananas being removed at time 5? Well, find f of 5. f of 5 straight from the calculator is 13.8. How quickly are the bananas being restocked at that same time? So this is the rate that they're being restocked at 5 hours. They're being restocked at 11.533 pounds per hour. Well, if they're being removed at this rate, but they're only being restocked at this rate, the amount of bananas on the table will be decreasing at time 5 simply because they're leaving more quickly than they're being placed back onto the table. So since f of 5 is greater than g of 5, bananas are leaving the display more quickly than they're arriving. Therefore, the number of bananas and the number of pounds of bananas is decreasing. How many pounds of bananas are on the display table at time 8? So you need to take into account how many bananas have been removed. You need to take into account how many pounds of bananas have been restocked, and you need to take into account how many pounds of bananas you started with. So it's a calculation here that, again, is easiest to carry out with the calculator. We start with 50 pounds of bananas on the table at the beginning of the day, minus how many pounds of bananas leave the display table from hour 0 to hour 8, plus how many pounds of bananas are placed back onto the display table by the store's workers. A little bit weird here because we have different limits of integration, but that's simply because we didn't start the restocking process until 3 hours into the workday. So the restocking only happened from hour 3 to hour 8, which is why you see the change in limits of integration there. But if you get this input to the calculator correctly, round it to 3 digits of accuracy, you're looking at 23.347 pounds of bananas on the display table at time 8.